Introduction to Symbolic Logic.
Definition 1. A proposition is any statement which is either true or false. Definition 2. The negation of proposition P, denoted by, now this symbol is sometimes called a tilde, but we read it as not. So we read this as denoted by not P, can be defined via the following truth table. So if you look at this truth table, P has two possibilities being a proposition. P is either true or false, and the negation of P flips the truth values. So true is flipped to false, false is flipped to true. So that's definition 2. Let's let P and Q be propositions, and definition 3, the conjunction of P and Q, denoted by P. Now this is actually read and it looks like an upside down V. So you read this as denoted by P and Q, can be defined via the following truth table. So let's make a truth table where we have P, Q, and we have P and Q. Now, there are two possibilities for P, true and false, and there are two possibilities for proposition Q, true and false. So if we list all these possibilities, we get true, 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 false, false, true, and false, false. Now, the order in which I listed all these possibilities doesn't matter. I just like doing it this way because it makes it easy to remember. True, 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 false, false, true, false, false. These are all the combinations that are possible, 4 of them. Now, the way to remember this conjunction, P and Q, is to think of this as a circuit. So like, let's say we have a little battery here, and we have a switch, and then we have another switch. And let's say we have some kind of like a light bulb. Looks more like a flying saucer, but that's supposed to be a light bulb. And I'm going to call this switch P, and I'm going to call this switch Q. And I'm going to remind everyone that this is an example of a series circuit. So this is an example of a series circuit. Now, if you think of electrons flowing through this circuit, you'll notice that both P and Q have to be in the closed position. And closed is equivalent to true. Or we could say on. Which is equivalent to true in this analogy, right? So if the P is on and the Q isn't on, well, the electrons won't flow. They both have to be on. So if you look at this, for this circuit to be passing electrons through, both switches have to be on, which is the same thing as saying both propositions have to be true. If either one of these propositions are false, the conjunction returns a false. So this is the easiest way to remember the conjunction of P and Q, which is more easily said P and Q. So there's only one way for P and Q to return a true truth value, and that is if both propositions are true. Okay, that's easy enough. Let's do definition 4. I'm sure you can figure out what that is. That would be the disjunction or the or. So definition 4. Let P and Q be propositions, the disjunction of P and Q, denoted by P. Now this looks like a little V, but it's a strange looking V, and it's not read V. This is actually read OR. Can be defined via the following truth table. So again, we have P, we have Q, and we have P or Q. And just like in the conjunction, since we have two propositions here, we're still going to have the same four truth values: true, 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 false, false, true, and false, false. Order doesn't matter, but I remember it easier this way. And the OR can be conceptualized as, surprise, surprise, a parallel circuit. So what we have here is we have a switch here, and we have a switch here, and this goes into our light bulb. And this is our battery, and I'll call this P, and I'll call this Q. And I would like to invite you to notice, make sure I'm in the frame, I would like to invite you to notice that if P is in the closed position, which is the on position, which is the true position, the electrons will flow. If P is off but Q is on, the electrons will flow. And if both are on, which means both are true, the electrons will flow. Some might flow this way, some might flow this way, but they'll still flow. The only way for this light not to be on is if both switches are in the open position, which is equivalent to false, right? So there's only one way for the OR to return a value of false, and that's if both are false. But otherwise, if both switches are on, we have a true, we have a true, and we have a true. So the easiest way to remember this is the parallel circuit. So far, we've done not, and or. We have another one for symbolic logic. Definition 5. So let's let P and Q be propositions, just as before. And I think I'm going to define two logical terms in one truth table, because if I don't, it could lead to confusion. So I want to actually define two together, and you'll see why I'm doing this. This comes from my experience teaching this subject. So the first logical construct that I want to define is if P then Q. If P then Q. And this is defined via a truth table. Defined via truth table. And I also want to define, I'll call this definition 6, if with two F's, P then Q, and the two F's is actually read if and only if. So if you've never seen this before, I'm not joking, you really can spell if with two F's, but you don't read it as if. You read it as if and only if. So it's shorthand. And so I want to put this in a single truth table just to show you what this looks like. And once we do that, we'll have the fundamental constructs of symbolic logic. And from this, we can pretty much do almost anything we need to do. So we're going to start with P and Q, just like we always have. I got to make sure this is in the frame. All right. So we're going to have if P, then Q, and then we're going to have if with two F's. P, then Q. So I'm going to define these two logical constructs together. So again, we have true, 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 false, false, true, and false, false. And the reason why I'm defining these together is because without defining these together, one of them could confuse you, but together you'll see kind of some sense in this whole thing. So when we have, this is called a conditional. It could be called a conditional statement. It could be called an implication. This is called a biconditional. So let me summarize what we did before I close this video. First thing we did was we defined a proposition as any statement which is either true or false, but not both or neither. Then what we did was, I used the wrong one. Here it is, right? Then what we did was we defined the term negation of a proposition, which we could call P without loss of any generality at all. And we denoted this not P using a simple truth table, just flipping the truth values. Easy. All right. Then the next thing we did was we really defined the term and. That's what we did here. We defined the term and we called it a conjunction. A logical conjunction. It sounds complicated, but it's really not that complicated. And we defined it in a truth table, and the way we can remember it is as a series circuit, because I'm not going to just remember the truth table, but if I conceptualize it through the analogy of a series circuit, I'm cool. I can remember this with no problem, and that is how I do it. And then the fourth definition we did was we actually defined the meaning of the logical word or, which sounds so basic, but it's not basic at all. And we used the analogy of the parallel circuit to do this, and we showed that there was only one way to return a truth value of false. And then the very last thing we did was we defined if P then Q, and we defined if and only if P then Q. We did it in the same truth table so that you could see the difference here. And I made a promise to you that I would make another video to really explain why these truth values are the way they are with a simple little example. And I'll do that in a separate video. But the P is sometimes called the premise, and the Q is sometimes called the conclusion. I'll just write CONC for conclusion. Sometimes the P is called the hypothesis. And sometimes the P and Q, I'm running out of room, but sometimes the P is called the antecedent. And sometimes the Q is called the consequent. So we have all these terms that you really do need to know because they fit in sort of different contexts. And so that's why we have so many different terms for these P's and Q's. But probably the most common term for P is premise, and probably the most common term for Q is conclusion in this conditional implication. So here's sort of an interesting thing. There's only one way, this is sort of interesting. There's only one way that this if P then Q can return a value of false, and that is if the premise is true and the conclusion is false. That's the only way. Otherwise, this implication has to be true. Now, you're probably going to ask yourself, why is that? I don't fully, completely understand, but that's a whole separate video. I will do a whole separate video on why these are the ones that confuse students. Probably this third line of the truth table is the one that confuses college students who are seeing symbolic logic for the first time the most. And I need to do an entire video on this, but all I'm doing is giving you the fundamental logical vocabulary to deal with symbolic logic. So you might need to pause this video about here and sort of say, there's only one way to return a value of false? What's with that? And I'll do another video and I'll explain that. Okay, so the biconditional, and there is a reason why we use this word bi, and I will show you that shortly. The biconditional implication is sometimes referred to as logical equivalence. equivalence. Logical equivalence. And what that means is that if the premise and the conclusion have the same truth value, we're going to return a value of true. So true and true, same truth value, we have a value of true. False, false, same truth value, we actually have a value of true. But when the truth values are different between P and Q, this if and only if returns a value of false. And this will be a separate video. A separate video for the conditional, a separate video for the biconditional. But what I will say here, kind of to leave you off with at least something to really understand before I close this video, which is already kind of long, is that the biconditional means that the two propositions are logically equivalent. That means if P is Q, if P is true and Q is true, the truth value is the same. They are logically equivalent. Same thing with the false, false, logically equivalent. And if we have an if and only if relationship between two propositions, another way to say this, which wouldn't be wrong, is P means Q. Because if every time P is Q, Q has to be true. And if every time P is false, Q has to be false. And if every time Q is true, P has to be true. And if every time Q is false, P has to be false, then essentially, logically, given that they are propositions, they mean the same thing. And this can actually serve as a way to define the term definition. What is the definition of the term definition? Well, really, we're in order to define the term definition, I know it sounds a little crazy, We need this concept of biconditionality, logical equivalence, and that's what this is. So before we go into symbolic logic in any more detail, these fundamental ideas have to be memorized.
A thumbs up would encourage me to make more videos like these, and a comment would be amazing.